In this video, we work problem 7.3.508.XP.MI from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following graph. It's given, the equation for this curve is given by y squared equals x squared times the quantity x plus 5, and that's this boundary. And we're asked to find the volumes of the solids that are generated when the loop of this graph is revolved about each of the following lines. So we're asked to revolve it about the x-axis, the y-axis, and the line x equals -5. I actually did part C in a different video last semester, so you might check that out on the homework help playlist if you're struggling with part C. But in this video, I'm going to do parts A and part B. So first we're asked, what is the volume of the solid of revolution that's generated when we take this loop and we revolve it around the x-axis. But first of all, notice that if you replace y with -y, -y also satisfies this equation. So even though I didn't do a very good job drawing it, this curve up here and this curve down here are supposed to be mirror images of each other, because when y satisfies this equation, -y satisfies that equation. So it should be very symmetric, even though I didn't draw it that way. When I create my solid of revolution by taking this and revolving it around the axis, we're going to see something that kind of looks like a Christmas ornament to me. And we are in the cylindrical shells section, 7.3 in our textbook. So we're going to find the volume of that solid of revolution that is formed by taking this and revolving it around the x-axis using the cylindrical shell method as opposed to other methods. So typically what we would do is we would graph the region and graph its reflection, but the region and its reflection are actually the same thing in this case. So we're just really drawing that loop again. I'm trying very hard to make it symmetric, but it's difficult to do. So we just do the best we can. I think I'm going to turn my paper sideways. That might make it a little easier. It's kind of like this shape. I don't really play cards, but kind of looks like a spade. I definitely don't play cards. Then we've got these lines over here. Because the loop, if it were being graphed parametrically, it would just be traced out like that. Okay, and now in part A, we're revolving this around this axis. And since we're revolving this region up here, I can think of it as just taking this region and revolving it around this axis. First, I will usually sketch my region, sketch the reflection, and turns out sketching the reflection is the same as sketching the loop itself. And then we slice the original region parallel to the axis, and then imagine taking that rectangle and rotating it around. Remember, whenever you're using the cylindrical shell method, you always want to slice parallel to the axis. If I rotate this around here, it would appear over here. And this is where making a symmetrical graph would make this look better. So say it's kind of like that, okay? And that's going to form a cylindrical shell. If I take that cylindrical shell, which looks kind of like this, and I slice it down one side and I unfold it, I get a rectangular slab. And the volume of this slab is the same as the volume of that shell. And if I can find the volume of one shell, I can find the volume of the entire solid of revolution. So in order to find the volume of this, I need two dimensions from this picture. I need the radius of the shell, so that's starting at the axis and going out to that representative rectangle. And I need the height of the shell. That's the distance from there to there. Okay, that height here becomes this height here. And this height here becomes this dimension, because I turned it sideways. And this radius is related to this distance over here. That's the circumference of that circle. So when I cut this down the side and I unfold it, the circumference, that distance, becomes this distance. The circumference is 2 pi times the radius. And this little width from there to there, that's the thickness of that slab. And that little width from there to there is the same as the width of the representative rectangle. So I draw my representative rectangle, I sketch the reflection about the axis that they mentioned, I label the radius, I label the height, and then I look at my representative rectangle and I think about whether the width of that rectangle is a tiny vertical distance or a tiny horizontal distance. Since it's a vertical distance, that's a delta y, which means that's a delta y, which means that's a delta y. And that means the volume of this shell is just length times width times height, which is 2 pi times the radius times the height times delta y. So I just need the radius and height in terms of y, and then we'll add those up and we'll take the limit as the number of shells goes to infinity, or alternatively as delta y goes to 0, and that's going to be enough to give us the integral that represents the volume of this solid of revolution. So I just need the radius and the height now. I'll do the radius first. The radius is a vertical distance. So we're going to take the top y value minus the bottom y value. And we want those in terms of y because we're integrating with respect to y. That's actually just a generic y value, so I'll call that top y value y sub I. And on the x-axis, remember y is equal to 0 there. So we just have y sub I for our radius. And then the height is going to be, well, it's this horizontal distance. It'll be x on the right minus x on the left. Oops. But x on the right minus x on the left, they're both actually defined by that same equation. It's x on the right minus x on the left, where x satisfies this equation. Y squared equals x squared times x plus 5. Ooh, I don't know if I want to do that. That's cubic in x. Do you guys know how to solve cubic equations in x? Well, you know how there's a quadratic equation? There's also a cubic equation. I don't want to have to solve that for y and get one version of the solution of that cubic equation in terms of y here, and then the other version of that solution of that cubic equation in terms of y here. Yeah, that's probably not the way to go. So even though we're in section 7.3, which is about the cylindrical shell method, I think in this case it actually makes a lot more sense to use the disk method. When I first drew this picture, I thought the disk method would be better, but I tried the cylindrical shell method because we were in 7.3. Now we see why using the cylindrical shell method is not a good idea here, because no one wants to try to solve that for x as a function of y. So I hope you don't feel like I wasted your time. We just spent a few minutes trying something and it didn't work. That's so much of what we do in mathematics, is we explore and we try things. And that's totally okay. And sometimes things that we try don't work out. Okay, I'm going to try to draw my picture again, and then rather than using the cylindrical shell method, which required me to solve for x in terms of y, I'm going to use the disk method. Actually, I think the disk method makes a lot more sense for this particular axis. So rather than slicing the original region parallel to the axis, when we use a disk method, we always slice perpendicular. So we're going to slice this way. Since there is no gap between that axis of revolution and the original region, we've got a disk rather than a washer. And the width or thickness of that disk is a tiny horizontal distance, so that is something in terms of x. So I sketch my region, I sketch a reflection across the axis, I slice perpendicular to the axis because I'm choosing to use the disk method or disk or washer method now, and then I look at my picture and I say, is it a disk or is it a washer? It's a disk because there's no gap between the axis and the region. And then I say, am I integrating with respect to x or y? And that has everything to do with the thickness of that washer or that disk. And the thickness is delta x because that's a little horizontal distance. So I can write my formula down. Volume is the area of that disk times the thickness. And if that is the radius r, well, the area of a circle is just pi r squared. And then we'll integrate with respect to x here. Okay, so with this in mind, I just need the radius in terms of x. Well, that's my radius. That radius is a vertical distance. So it is the top y value minus the bottom y value, but it's still in terms of x. And I'm on this curve where y is equal to x squared times the quantity x plus 5. So the top y value comes from taking the top y value in terms of x comes from taking this equation and solving it for y by taking the square root of both sides. So let's do the algebra there. You've got y squared equals x squared times the quantity x plus 5. And we take the square root of both sides, don't forget the plus or minus, and you get y equals plus or minus the square root of x squared times x plus 5. Okay, now y is positive, or it's greater than or equal to 0 up here on the top half of this curve. When I think of creating a solid of revolution by revolving this region about the x-axis, I'm really focused on this top half of the region anyway. And I'm thinking about taking that and revolving it around. So I'm thinking of this as my region rather than thinking of the whole thing as my region. With that in mind, y is going to be the positive square root there. Then y equals the negative square root down here on that bottom edge, but we're not too concerned about that. The top y value here is the positive square root of x squared times the quantity x plus 5. And the bottom y value for that region is just y equals 0. It's not this, because remember the radius starts at the axis and goes out to that outer edge. So I've got that top y value minus the bottom y value, which is just 0. Those are all evaluated at some x value on the ith interval. And we get this. Now, the square root of x squared is always positive. Because if I take 2 and I square it, I get 4, and then if I take the square root of that, I get 2. So this squaring function and the square root function, they undo each other, and you just get 2 back as long as that number is non-negative. But if the number is negative, -2 times -2 is +4, and the square root of +4 is 2. We don't get -2 back here. We get +2 back. So in general, the square root of x squared is the absolute value of x, and the absolute value of x is just x if x is greater than or equal to 0. But if x is negative, if x is a negative number, so like -2, I don't get x back, but I get the negative of -2. So it's going to be a negative x when x is negative. Now, a lot of people think, I thought absolute value is supposed to be positive. Why is there a negative there? And it seems like that's a negative value, but it's not. Remember, because x is negative, so that's a negative times a negative, which makes that positive. And if x is positive or 0, then that's a positive number, except for when it's 0. Okay, so the square root of x squared is negative x when x is negative. And look at our region. X starts at -5 and goes to 0. So we're talking about this, except for when x is 0. So this radius can be rewritten this way. The square root of x squared is -x. And then you've got the positive square root of x plus 5 there. Just take the square root of that part and the square root of that part and you simplify. Okay, well, it actually doesn't change things much because we're going to square it anyway. That is necessary in part C, but since we're squaring it anyway, it doesn't matter much here. Okay, so the volume of the ith disk is pi times the radius squared times delta x. You've got a product squared, so you can square the first factor, -x times -x. It's positive x squared, and that square root squared, it's just going to give you that x plus 5. And then we will add these up, and we'll take the limit as the number of slices goes to infinity. Number of disks goes to infinity, or alternatively, if you prefer, you can say that delta x goes to 0, or you can make all of your delta x's different depending on the interval and let delta x by, like make all of those go to 0 at the same time. And then we get an integral. So we have, this is pi times x squared times x plus 5. We're integrating with respect to x. And we integrate from x equals -5 to x equals 0. We always get the bounds from the original region. Oops, smallest to largest, -5 to 0. So let's work this out on the next page. This is for part A. Pi is a constant, you can factor that out. I would distribute the x squared. Then here you want to add 1 to the exponent and divide by the new exponent. Bring the 5 down. Add 1 to the exponent and divide by the new exponent. Substitute in -5 and 0 and subtract. You plug in 0, you're going to get 0. Then you're going to subtract this evaluated at -5. So we're going to have -pi times 1/4 times -5 to the 4th plus 5/3 times -5 cubed. And we'll use a calculator for the arithmetic. So that's -5 to the 4th, which is the same as 5 to the 4th, divided by 4, minus, that's going to be a -5 to the 4th, divided by 3. So I get a negative number, but then I multiply it by -pi, and I get 625 pi over 12. So that was part A. Now let's do part B. We're going to take this same region, except instead of revolving it around the x-axis this time, we're going to revolve it around the y-axis. And this time, I think cylindrical shells actually does make a lot more sense. I'm trying to draw that shape again. It's hard to draw. My dad is an artist, and I wish I had his skill right now. Here we go. Kind of butterfly shape. It looks like a bow tie. Now, the volume of the solid of revolution would not look like a bow tie, but kind of looks like that in 2D, doesn't it? Okay, so we've got this region and we revolve it around the y-axis. And that's always what you want to do. You want to sketch your region. Then you want to sketch the reflection across the axis. And then you're going to slice it. You can either slice parallel to the axis and use the cylindrical shell method, or you can slice perpendicular to the axis and use the disc or washer method. Now, if we slice perpendicular to the axis and try to use the disc or washer method here, we're going to end up with needing to find x's in terms of y's. And remember what happened over here when we had to find x in terms of y in this equation? It was hard to do because it's a cubic equation in x, and we didn't want to have to use that cubic equation formula. It's kind of like the quadratic formula, but for cubic equations, we don't want to have to do that. So rather than slicing perpendicular to the axis to get washers, let's slice the region parallel to the axis. And then we will revolve that rectangle around the axis. And draw a typical cylindrical shell. Okay. So now we just need to find the volume of the shell. If we can find the volume of the shell, we can find the volume of the solid of revolution. So the first thing I do when I want the volume of the shell is I label the radius and height. So the height is actually this distance from here to here. And the radius starts at the axis and it goes out to that representative rectangle. Now it goes out to this representative rectangle in the original region, not in the reflected region. We don't want to use this rectangle, that distance there. We want to use this distance here. So we've got our shell. It looks like this. Sorry, I'm having a really hard time with my pictures today. And then we slice it down one side and we unfold it, and it looks kind of like this. And this is the height, and that height becomes this height. And this is the circumference of that shell, and the circumference, when you unfold it, becomes this dimension. And then the width of that comes from the width of that rectangle. And the width of the rectangle is a tiny horizontal distance, so that is a delta x. So the volume of this is the same as the volume of this. And if we can find the volume of one of these, we can find the volume of the whole thing. So volume is length times width times height, which is 2 pi times the radius times the height times delta x. Now we just need to find the radius and height in terms of x. Okay. So let's do the height first. That's a vertical distance, so we're going to use the top y value minus the bottom y value. And again, we're using this y squared equals x squared times x plus 5 as the equation of that entire curve. Now if I solve that for y, trying to find a space to solve that for y, let's do it here. I'll have y equals plus or minus the square root of everything on that side. Okay, so on the top half, y is the positive square root. Actually, I'll leave that alone for right now. On the top half of this curve, y is the positive square root because y is positive up here. And on the bottom half of that curve, y is the negative square root. So I write down y top minus y bottom. What I'm writing down is that positive square root minus the negative square root. and subtracting a negative is the same as adding. So we've got 2 of those. And then for the same reason that we talked about earlier, since x is negative over here, the square root of x squared, that's the same as the absolute value of x, we get a negative x back. So if I take the square root of this piece and the square root of this piece, the square root of this piece is a negative x sub I. This one can't be simplified, so we'll leave it alone. So that is our height. Now if you're saying to yourself, the heights are supposed to be positive, you're right, they are supposed to be positive. This square root's always positive. That 2 is always positive. And since x is negative here, this negative times that negative makes that height positive. So this is actually a positive number, which is giving us the height of a cylindrical shell, even though it's got a negative sign out front. Okay, and then for the radius, it's a horizontal distance. So it's x on the right minus x on the left. And x on the right is 0 because x is equal to 0 when we're on the y-axis, right? This is x equals 0. And then x on the left is just x. And again, we've got a radius which is negative x. And you might be thinking, well, that's a negative number, but it's not because x is negative. So this is a negative times a negative, which makes that radius positive. Okay, and then you multiply all these guys together. That negative times that negative makes a positive. That 2 times that 2 makes that a 4 pi. So we've got 4 pi. And then we've got an x times an x is x squared times the square root of x plus 5 times delta x. And that's the volume of one of our cylindrical shells. The total volume is the sum of all those volumes. We'll add them up and take the limit as delta x goes to 0 or as the number of shells goes to infinity, and we get an integral. Okay, so we'll write this down and then we'll evaluate the integral. I'll just do this. Okay. So that's the integral of 4 pi times x squared times the square root of x plus 5 with respect to x. And remember what our region looks like. The region looks like this. So x ranged from -5 to 0. So those are our bounds. Now there are lots of ways you could evaluate this integral. You could use integration by parts if you choose to. I think u substitution is probably the simplest, but it's kind of a fancy u sub. So let's talk about how to do a fancy u sub here. Now, if I let u be x plus 5, it turns out I can write this integral entirely in terms of u. Now, if you compute du, you might say, well, you just get 1 dx. You might say to yourself, well, how does that help me get rid of this x squared? The truth is it doesn't. But since I have u in terms of x right here, I can also find x in terms of u by subtracting 5 from both sides. And so that x squared can be rewritten as u minus 5 squared because x and u minus 5 are the same thing. So even though this might indicate to you that u sub won't work, actually, since I can get x in terms of u right here, u sub is going to work great. So we're going to have the integral of 4 pi times whatever x is in terms of u squared times the square root of u. That's u. X in terms of u is u minus 5. And dx is the same as du. And if you're saying to yourself, I can't evaluate that, you're right, you can't evaluate this in the current form. We don't have a basic rule for this product, but you can FOIL this and then multiply by the u to the 1/2, just using exponent properties. And then this will just be a power rule problem as far as the anti-differentiation is concerned. Now, these bounds here represent x values because we're integrating with respect to x. This says start at x equals -5 and end at x equals 0, which is consistent with the picture of our region that we were looking at, that loop. It started at x equals -5 and ended at x equals 0. But if I'm changing this integral to 1 in terms of u, in order for this to be equal to this, I need u bounds here. I can't use x bounds here. So I need to replace x with 0 and -5 here to find the corresponding bounds for u. A lot of people forget this step, and I understand it's easy to do. So replace x with 0. When x is 0, u turns out to be 5. X equals 0 was our upper limit, so our new upper limit is 5. And x equals -5 was our lower limit, so we substitute that in for x. And then we've got u equals -5 plus 5 when x equals -5, so we get 0. So that's our lower limit. And now since we've changed the bounds, we never have to go back to x. We just simplify this, integrate, and evaluate from 0 to 5, and that's going to be the volume of the solid of revolution. So I'll take out the 4 pi. I'll write that u minus 5 twice in FOIL. I'll write that square root of u as u to the 1/2 power. So remember how that works. The index of the radical goes in the denominator. Whatever power is there goes in the numerator. So there's an implied 1 there. With a square root, there's an implied 2 there. So that makes this a u to the 1/2 power. I'll write this twice in FOIL. First times first is u squared. Outer times outer is -5u. Inner times inner is another -5u. So we have -10u plus last times last, which is 25. So you can do that, or you can remember this old rule from algebra. You can always apply that as well if you remember it. That just comes from writing that twice and foiling. And then over here, I'm just going to distribute my u to the 1/2 to all of these guys. And just remember, if you have two exponential type expressions or power functions with the same base, you've got something raised to a power. If the base is the same, you keep the base and you add the exponents. So we'll have u squared times u to the 1/2 is u to the 2.5, or u to the 5/2. Add the exponents there as well. 1 plus 1/2 is 3/2. And then we've got that right there. All right, now we've got rules for that. So we will anti-differentiate, add 1 to the exponent and divide by the new exponent, bring the -10 down, add 1 to the exponent and divide by the new exponent. Dividing by 5/2 is the same as multiplying by 2/5. Bring the 25 down, add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is multiplying by 2/3, and evaluate from 0 to 5. 5 goes into 10 twice, and you've got a 50 there. So we've got 4 pi times 2/7 times something to the 7/2 minus, looks like 4 times something to the 5/2 plus 50/3 times something to the 3/2. And we evaluate this at 5 and 0 and subtract. So at 5 we get this. And if we substitute in u equals 0, we get 0. So we're subtracting nothing. So this is our answer. It's just not simplified. If you want to simplify it, you can. Now, the way I'm tending to think of this is I'm thinking of this as 5 to the 3.5 power. Do you see that? 7 divided by 2 is 3.5. So that would make that 5 times 5 times 5 because of this property. That 3.5 can be split into 5 cubed times 5 to the 1/2. So that's 5 times 5 times 5, which is 125, times 5 to the 1/2, which is the square root of 5. We have -4, and this is 5 to the 2.5 power, So that's 5 to the second plus, or times 5 to the 1/2 using that rule. So it's 25 times the square root of 5. And here, well, that's 5 to the 1.5. So it's a single 5 times the square root of 5. And so we get, well, we've got a bunch of square roots of 5 everywhere. 4 pi times 250 over 7 times the square root of 5 minus 100 times the square root of 5 plus 250 over 3 times the square root of 5. Of course, you could just do this in your calculator. We want an exact answer for WebAssign though, not a decimal approximation. So make sure you work out that exact answer. So I'll just do this 250 over 7 minus 100 plus 250 over 3. And that's just the coefficients here. All of those are multiplied by square roots of 5. So I've got 4 pi times 400 over 21 times square root of 5. So that's 1600 pi times the square root of 5 over 21. And if you're saying to yourself, what is that? It's the value of that integral. And what is that? That is the volume of this. It looks like a bow tie. I actually think of it as a Christmas ornament on this side and sort of a symmetrical thing on this side. It's like a Christmas ornament that kind of looks like a rounded hourglass. The volume of that is this number. And remember, pi is about 3.14, and square root of 5 is just going to be a little bit more than 2. So that's actually a number, and it's that many units cubed. That's the volume of the solid of revolution. So we took this region and we revolved it around the x-axis. We tried to use the cylindrical shell method, but that would require solving this equation for x in terms of y, so we decided not to. We said, rather than do that, let's just use the disk method. So we used the disk method for when we took this region and revolved it around the x-axis. Then we said, okay, what about when we revolve it around the y-axis? Well, when we revolve around the y-axis, it made a lot more sense to use the cylindrical shell method, because I can get the radius in terms of x and the height in terms of x pretty easily, whereas finding an inner radius and an outer radius, if I had sliced the other way, would have required finding x in terms of y with this equation, which again is hard. It's cubic in x. So I didn't want to do that. Instead, we use the cylindrical shell method. Now there's one other problem for this problem, which I believe is problem 10 in your homework. And it's about a different line. It's x equals -5 on one student's assignment. It might be x equals -6 on yours, or x equals -7, but the principles are exactly the same. If you want to see that problem, look at another video. It's already been posted in the Calc II Homework Help playlist. Please let me know if you need anything or if you have any questions about this. Bye for now.